Hi everyone. Today we're going to be learning about measurement and significant figures and density. We're going to see how when you make a measurement there is some uncertainty to it, and we can keep track of that uncertainty as we go through calculations by keeping track of the number of significant figures, first in our measurement and then in the result of each part of our calculations. And we can do all this while also learning to calculate for density and dealing with different units. All right, so here's the example problem. Let's say that we have a paper clip. You can put it next to a ruler, which is measuring in centimeters here. And so that you can see this more effectively, I've kind of expanded this ruler so that here is our new expanded version of the paper clip. You can see that the paper clip, its length goes somewhere between 3 centimeters and 4 centimeters. It goes, let's see, 3.1, 2, 3, 4, 5, 6, somewhere between 3.5 and 3.6. Now, you would not want to mark that this is a 3.5 centimeter paper clip because then the reader might assume that it's just somewhere between 3 and 4. You see, when we make a measurement, we will record always one estimated digit. So if we feel confident that this goes beyond that 3.5, then we know it's 3.5 something. We can add another estimated digit. Here, maybe we can call it 3.52. That too is our estimated digit. Always have one estimated digit. Okay, so now we've found the length of this paperclip. We also have measured the mass of the paperclip, and we've determined by looking it up the density of the paperclip, 7.70 grams per centimeter cubed. So the objective is to determine the radius of the paperclip in millimeters. So we know the density and the mass of the paperclip. We also know the height of it, the length of it. So if we can find the volume of it, having density and mass, and knowing the height, we can then calculate the radius, because we'll see in a moment that the volume ends up being equal to pi r squared times the height. Okay, so first, let's calculate that volume, keeping the appropriate number of sig figs. So we know that density is equal to mass over volume. That's an equation you should commit to memory. And that can be rearranged to give volume is equal to mass over density by multiplying both sides by volume and then dividing both sides by density. So now we can start plugging into that equation. We know the mass is 0.320 grams. I know the scale read 0.320 grams. I should not write 0.32. That would mean that I don't know the mass of this very precisely. If I wrote 0.32, I would be implying that that 2 is estimated if it were my last digit. So that mass would be somewhere between 0.3 and 0.4, and just generally that. But by keeping that 0, which I got from an expensive scale that costs hundreds of dollars, it's more expensive because it's precise. You know, because we have such an expensive scale, we want to mark that we were able to measure the mass to the thousandths place. So we're not going to give up that 0 that we paid for. All right. So we have 0.320 grams, and then we divide by the density, which is 7.70 grams. Yeah, don't leave out zeros. That was the density found on online. Okay, so from that we can calculate the volume. Now, your calculator might spit out that the volume is 0.041558 grams per centimeter. Actually, no, just centimeters cubed. But if you were to write that number, you would be implying that you know pretty darned well the volume of this. But it turns out we were only able to record the mass to 3 significant figures, and we knew the density only to 3 significant figures. When we do multiplication or division, the result should be limited by the smallest number of sig figs that we had. If we divided 3 sig figs by 3 sig figs, the smaller number of sig figs is 3. So we need to round this volume to have just 3 sig figs. So we can take this number that came out of that calculator and then round it so that we get 3 sig figs. Cross that out, cross that out. Why am I using these as my significant figures, and why not this 0 or that 0? Zeros to the left of non-zeros are never significant. But going up top, zeros to the right of non-zeros are significant if there's a decimal shown anywhere. So these zeros are not significant. So if I need to have 3 sig figs, I'll do this 4, this 1, and then let's see, rounding the 8 and the 5. That this number is 5 or greater, so this will round up. Overall, the answer is closer to 0.0416. So we round to 0.0416, and that is the volume of the paperclip. But of course, this is kind of a small number, so here's an opportunity to practice converting into scientific notation. In order to get into scientific notation where we have 1 digit to the left of the decimal, we need to move the decimal twice to the right. And so, kind of going down the staircase, which maybe you remember from a couple years ago, if you're going from 10 twice to the right, you go from 10 to the 0 to 10 to the -2. There's a whole video on this in the supplemental videos below this. Okay, so we have the volume of the paperclip, and we can convert and find the radius. However, we are asked to find the radius in millimeters, so we might as well convert this volume from centimeters cubed into millimeters cubed. Another option later would be to find the radius in centimeters and then just convert that to millimeters. That's another way to do this, but the slightly more complex way, this is an example for me to teach it to you, is to convert from centimeters cubed to millimeters cubed. I need to know the number of millimeters cubed per centimeter cubed. Now, maybe you know that there are 10 millimeters per centimeter, right? You know, a centimeter is 100th of a meter, and a millimeter is 1,000th of a meter. So there's 10 times more millimeters than centimeters. But to know the cubic relationship, we need to take both sides of this equation and cube them. So you get 1 centimeter all cubed, that gives you 1 centimeter cubed. And you take 10 millimeters all cubed, and that gives you 10 to the 3 millimeters cubed. So we are able now to use that relationship to convert from centimeters cubed to millimeters cubed using this unit conversion factor. You know, so now the centimeters cubed is on top and bottom, it crosses out, and we're left only with millimeters cubed as our unit. So we can now plug in to find the radius. Hopefully you've kind of memorized that the volume of a container or shape is equal to the area of the base of that container times its height. So if our let's see, if our paperclip is a cylinder, then its base is a circle. So the area of that base is pi r squared, and then multiplied by the height of that paperclip, or its length. So you get this equation, and then you can rearrange it to solve for radius. So, you know, divide both sides by pi and height, and then take the square root of both sides. There you are. And now you can plug in. The volume of the container is 41.6 millimeters cubed, and we plug in pi, and the height was in 35.2 millimeters. Now I know above we wrote it was 3.52 centimeters, So we had to multiply by 10 to convert into millimeters. So you can now, figuring out what units are left over, we had millimeters cubed, and then we divided by millimeters. So that gave us millimeters squared, but we also were taking the square root of all of that. So the square root of millimeters squared is just millimeters. So we got our radius in millimeters. Oh, it's tricky to deal with units. You'll get a bit of practice in this in the practice problems. So just one kind of final brief topic. Let's say that you were to wanting to find the mass of some solid chemical, knowing that the container it was in had a mass of 1.20 grams, and with the container, the mass of that solid chemical was 11.40 grams. Determine the mass of that solid chemical. Well, you can do that by subtraction, right? So, the difference between the mass of this and the mass of all this is just the mass of that solid chemical. So your calculator says the mass is 10.20 grams. But how should you report this to keep track of the level of precision of your scale? Should you keep track of sig figs? Actually, no. We do keep track of sig figs when we're doing multiplication or division, but when we're doing addition or subtraction, what we care about is just the place of our measurements. So this 11.40 grams, that went to the hundredths place. And this 1.20 grams, that went to the hundredths place. So we get to go to the hundredths place for this subtraction. And so we get 10.20 grams. That's weird. That's the mass of it. Even though there were only 3 sig figs in this number, we get 4 sig figs in our result because we don't care about sig figs at all. When it's about multiplication or division, we just care about the place that the scale went to. So just kind of writing that out. With addition or subtraction, the answer should go to the furthest right agreed upon place. In this case, both of these numbers went all the way to the hundredths place, so our answer gets to go to the hundredths place. All right, thank you for watching.